Deep learning in Daba. So we've got 2 more hours of fantastic talks and prize giving, and then we're all going to jump onto the party bus to Safari Park. But before that, there are a few announcements. First of all, if you stayed in the hostels and you still need to pay cash to us or for any other reason, please meet Elizabeth outside this session. Secondly, for the closing event tonight, we are going to go to Safari Park Hotel. The buses are going to leave outside this parking lot. I'm lying. Okay, the buses are leaving outside the EBR parking lot at 6:30. Don't be late because we won't wait for you. First bus is back at 10:30. Next, if you want to eat, if you want to drink anything, if you want beer or wine or cool drink, please pick up your coupons as you climb into the bus. Otherwise, you'll have to ask your friends at the party. Next, there are extra Indaba bags and extra T-shirts and things left over, so just ask us afterwards. Actually, they'll be on the table outside. Then, I'm sure some of you lost things and have not found them again. There's a table at the back for lost and found, so just go and look on the table. I've picked up plenty of bits and pieces of electronics that no one has claimed yet. So if you've lost something, look at the back. Next thing is, if you're staying in the hostels, checkout and breakfast are different tomorrow morning. Checkout will be at KUCC. Okay, if you're in the hostels, raise your hand. Where are you going to deposit your key tomorrow morning? KUCC. Okay, we're having breakfast. Lastly, airport transfers, everyone just coordinate on Slack. Cool. So everyone, we have a guest speaker before our keynote speaker. I'd like to introduce you to Ayana Wanyika. Ayana, would you like to come to the stage? So Ayana is 9 years old. So her career has started a bit earlier than some of yours, including mine. She is East Africa's youngest climate change ambassador. She goes to Peponi School in Nairobi, and in the next few minutes she's going to talk to us about why climate change, education and health are really key issues for the AI community to address. So Ayana, over to you.
Okay. Good afternoon, ladies and gentlemen, my fellow teens in AI. Machine learning gurus, all protocols observed. My name is Ayana Wanyika Klastengadai. I am East Africa's youngest climate change ambassador and Kenya's youngest Mashujaa. My speech today is titled Machine Learning and AI for Sustainable Impact on Climate Change, Health and Education. My name is I am 9 years old student from Peponi School, Kenya's youngest climate crisis ambassador also. I use social media to create awareness about nature, so please follow me on Twitter, Instagram, Facebook, and subscribe to my YouTube channel. I am humbled and excited to speak to you today at this Deep Learning in Daba conference. God forbid, if you get cancer in Africa, you'll sell even your children's clothes to pay hospital bills. Same with education. When a student is admitted to university, you should see the relatives falling over each other to do fundraising for school fees. But can Africa leapfrog development using machine learning and artificial intelligence to provide sustainable solutions for the continent? When I was 4 years old in kindergarten, we did a project on heroes. These heroes included Martin Luther King, Henry Wanyoike, Uhuru Kenyatta, Florence Nightingale, Barack Obama, Wangari Maathai, and Nelson Mandela, and Mahatma Gandhi. I really liked Wangari Maathai's tree planting, so I initially started planting trees at home. Then in Karura Forest, 10 became 30, then 30 became 50. And now I have planted 1,538 trees. And thousands more with students from different schools. I have since founded Children with Nature, and we go to schools educating students on climate crisis, deforestation, wildlife conservation, plastic pollution, and blue ocean economy. We have set up over seedlings in 79 schools. Today, I'm excited to tell you that I will be talking about machine learning in schools, coding, and other tech solutions. I will join Gakuo, Amusaka, and all the coding community every Saturday to develop my machine learning skills. If in 1999, Kenyans had very few landlines, yet now mobile phone penetration and M-Pesa has become a global phenomenon, this means you can be the solution for health, education, and climate change. AI can predict cancer, resurgence, hurricanes, droughts, forest fires can be predicted with deep machine learning. Don't tell anyone tell you that you are so young or too geeky. 60% of Africans are below the age of 35. Why would the politicians, teachers, diplomats telling us we are just children, we should be in school? The African Union calls us the youth, Africa's demographic dividend. The youth around the world are ready to get hands dirty and work. We are full of bright ideas, full of energy. We are digital too. We understand coding, machine learning. During the Regreening Kenya launch by Dr. Fred Michangi, my friend, they set up a target of 50 million trees planted by 2020. If they targeted 3 trees per student and every youth below 35 was given the 3 seedlings and shown where to plant, this target would be achieved in 3 days. Just 3 days. Just do the math. It's not rocket science. With technology, it could also be achieved in a few hours. Would you like to brainstorm about this? I am happy to see that the Indiba conference has made a choice to increase teens' participation in machine learning. Thank you for teaching us AI. We will accelerate the global sustainable development goals using tech. Creating networking platforms like this for a vibrant youth will bring transformational change towards sustainability. I will leave you with a quote from Greta Thunberg. If a few children can get headlines all over the world just by not going to school for a few weeks, imagine what we could achieve together. With that, I would like to wish Indiba all the youth around the world a huge success in conservation. Asante sana, and may God bless you.
Thank you, Miraj Shilan. We have something from Visa for you. I'll just quickly hand it over.
Thank you.
There we go. Ladies and gentlemen, I'd now like to introduce you our final keynote speaker, Professor Samory Kpotufe. He's an assistant professor at Columbia University in New York. He's an African. He hails from Togo. He's done fantastic work in non-parametric Bayesian methods, in learning theory, but today he's going to speak to you about something completely different. Everyone, please give a big hand for Samory.
everyone. First, I would like to say thanks for the organizers of deep learning in Daba. I kept hearing about deep learning in Daba, and I'm glad that I finally came. I was so excited last time, actually. I was at the poster session, and just seeing so many interesting ideas through the posters, and it just makes me proud of being African right now. So thanks again to the organizers. Today I'll talk about a problem that somewhat touches upon much of the problems that were discussed throughout the week. So I'll talk about transfer learning. I'll first start by defining transfer learning. Much of my work is theoretical. It's very mathematical. However, I felt like, okay, since it's the last talk, I probably should reduce the math and try to give much more intuition. It actually helps me to reduce the math because I'm still jet-lagged. And so I'll try to give intuition about the problem and try to sort of motivate the problem using various, some of the examples that people have presented so far. But first, what is transfer learning? It's just a very generic term that people have been using in machine learning to sort of cover many different problems that sort of are similar to what humans do all the time, right? Humans somehow are able all the time to transfer knowledge quickly between related problems and related tasks. And so various problems, sub-problems in machine learning touch upon that. And we call that whole field transfer learning. Just again, to appeal to your human intuition, think about this following fact, that a small child, and we had a beautiful child a second ago, a small child is able to quickly transfer information from a problem to another. You teach a child to draw, they quickly learn to actually paint, right? The tasks are somewhat related, and they can quickly do it. And one of the questions in machine learning is whether we can implement similar knowledge transfer, right? Such fast knowledge transfer. Can we transfer knowledge the way humans do? This is sort of a grand goal of machine learning. I feel like we are very far from there, but we can start working towards it. So the general problem is people call it transfer, some people call it domain adaptation, and there are various names associated with the problem. But I hope this intuition is clear to everyone. We learn something, and then there is a related task, and we are able to quickly start performing the related task without getting too many examples of the related task. We had a lot of examples of one task, and we want to do the related task, but we don't need that many examples anymore, right? So that's sort of the problem. So today I'll focus on the sub-problem of transfer. And this sub-problem is of general relevance, and I'll call it covariance shift. I'll define covariance shift a bit later in more mathematically, but for now, the definition I'll give is a simple one. I'll say that we train on data from a particular population. However, we want to transfer the ML technology to a different population that we did not train on. Somehow, we imagine that the populations are somewhat related, right? So here is an example. Imagine that we have vision software trained in the US on a lot of data collected on images from the US, right? And this vision software, we want to transfer it and we want to deploy it here in Kenya, right? The images are different, and however, we don't want to have to retrain in Kenya. We don't have to recollect a lot of images in Kenya in order to deploy this vision software out here, right? So that's the problem of transfer. That's the problem of covariance shift. We have a population from which we sample, and there is another population somewhat related that we want to transfer the knowledge to. All right. So here, as I said, I'm going to try to appeal to some of the examples given before. You might recognize this picture from before. So even in the US, the problem doesn't even have to be that we're transferring from the US population to the Kenyan population. Even in the US, the problem exists, right? We saw this problem last time, and the problem we had here is that much of the images that are trained on are images collected on the internet, and these images don't necessarily contain certain subset of the population are not as represented, right? So this is very well known. It's known racial and gender bias in vision software. It turns out that the problem is even worse for females than for males. And it doesn't have to be black females. It's actually females of dark skin. They are hard to recognize. 35% of darker skinned women were misidentified by Microsoft Vision not so long ago, 2018 even, right? Here is another example, and this is actually from last year also, and this is in China. iPhone X is unlocked by the wrong Asian person, yeah. So, again, we see what the problem is, right? The iPhone, unfortunately, trained their software on images that don't contain enough Asian people, right? And so that's the thing. Again, one thing that I would like you to keep in mind is we train on a population, but there is another target population on which we want to deploy, okay? So the same problem in many critical applications. Here, this is an application that really bothers me because it has a huge societal effect and ethical implications. AI for judicial systems. It's unfortunate, but it's actually being deployed. And I don't believe that this thing should be deployed yet. But people are deploying it. And the type of things they deploy it on is judges have just too many cases to handle, right? And they'll decide whether they give bail to a particular defendant, and they want to assess the risk of this defendant. The one problem is that the source population on which these things are trained are prison inmates, people that are already that were already found guilty, right? Because that's the cheap data that they can have access to. And the target population is actually everyone that's been arrested, everyone that's in front of the judge, guilty or innocent, right? So two different populations we want to be able to transfer from one population to the other. Here is some statistics on it. 60% of inaccurate risk assessment on things that are being used today. That's really sad. And this was in a recent study by ProPublica. You can find it online. You can imagine that similar problems exist in other applications of high impact, right? AI in medicine, genomics, insurance industry, and name it. Many of the applications we want to work on would have this sort of problem. And the main reason why is because it is very hard to obtain the right type of data, right? The main reason why is, and it has nothing to do, personally, I don't believe has much to do with racism, it has to do with finance, with how costly it is. So the issue for me, I believe most of the time is just a financial issue. Companies have a hard time obtaining the right data, the target data. And I'm going to use this term, source data and target data. Source to say the population on which we train, and target data for the population that we want to actually target, okay? Target data is often hard to obtain, and that's really the problem. So that to me is a really nice thing to realize, because that means we can probably solve it. Because if it's hard to obtain, maybe we just have to find ways to make it cheaper to obtain, right? We have a certain number of target data we might have to sample. Maybe we can reduce that. Maybe we can sample a lot less. Maybe we can find solutions that help us sample a lot less of the target. And I'll keep making these points clear throughout the talk. But to put it in perspective, I'll tell you how I started thinking about the problem. I live in the US, I use an iPhone, and Siri has never been able to understand my accent, right? And somehow I was thinking about it. Over time, he started doing better, but it took him about 5 years to get better. And that means it was expensive for them. They had to start sampling more various accents within the US, and that's costly. And that's actually one of the main obstacles, right? So can we find a way to reduce the cost? And what I mean by that is, given so much training that they already have, can we find solutions that allow them to use very few target data in order to still do well on the target, right? And so this has sort of been one of the basic problems in transfer. There are many other problems in transfer, but this is one of the basic ones. Can we make it cheaper? All right. However, that brings right away the next question. how much target data is enough, right? This is just another way to ask the same question. How much target data is enough? And that's where we have to try to quantify this, and that's where mathematics is coming in, right? Okay. Another way to ask the same question is to say, how much information was in the source already about the target? And again, this is where mathematics has to come in. We need to be able to quantify this notion of information. What information is there in the source about the target? All right, so I'll start formalizing things. This is where I'm getting into math. I'll start formalizing things. And I'll start slow and then formalize a lot more. So we'll assume that we are in classification. Classification is one of the most important problems, so we'll start with classification. Actually, we'll stick to classification throughout this talk. We're in classification. I want to map a particular feature vector to a label or class, right? So imagine the feature vector is describing an image, and and the class is the object that is in the image. I want to do object recognition, for instance, right? All right. So next, we are going to view the source population and the target population as probability distributions. Then the question becomes sort of how far is one probability distribution to the other, or how much information is there in one probability distribution. And again, I'm going to emphasize something, is that the distribution is over the joint pair, right? X and Y, the covariates and the label, the set of features and the label. All right. So I'll use a small cartoon to illustrate things, and I'll use the same cartoon throughout. Here, I'm going to imagine, I don't know if this thing is working, whether you can see this. Yeah, sort of? Okay, good. So this is the source distribution. This is the usual thing in machine learning. I have a source distribution, and you can imagine that there is a lot more squares here, a lot more triangles here. I got lazy drawing this thing. And so that's the source distribution. And what do we do in machine learning? We sample from this source distribution. Recall, we don't know the source distribution. It's a population. It has so much in there. We don't know it. We sample from it, and then we try to do well relative to it. You can imagine here that the squares represent, for instance, a particular type of accent, right? Let's say that this is the space of accent, speech signals in the US. The squares represent a particular type of accent. The triangles represent a different type of accent. Maybe the triangles are African accents, right? And the target distribution, let's say it's Kenya, it has a lot more African accent and fewer American accents, right? And that's what we call in covariance shift. The proportions have shifted from the source to the target. In normal machine learning, we obtain the small sample, and then we just need to do well with respect to this population. Now, we obtain this small sample, you see a particular proportion, another proportion, and we want to do well with respect to this one. However, we haven't observed enough of this. Fine? All right. Again, covariance shift. PX now being just the distribution of the X's, of the images here, or of the speech signals. PX is different from QX. However, we sort of assume that once we see, let's say it's an image, once we see an image, we know the object in it. So P of Y given X and Q of Y given X are the same. Only thing that's changing is the proportions, the relative proportions between the populations. All right? Okay. So here are some of the basic questions we want to answer, not just as theoreticians, but as practitioners. We want to answer these basic questions. First question is there enough information in the source P about target Q? And I'll keep repeating, I'm repeating myself, but I'll keep repeating myself till I'm sure that everything is clear. Is there enough information in the source P about the target Q? And that brings up right away a question, what do we mean by information, right? The next is, if there is not enough information in P about target Q, that sort of means that we need to acquire more target data. So then, how much target data do we need to acquire? Next, would unlabeled target data suffice? Or at least would it help? Why this question? Because it turns out that unlabeled data, the distinction between unlabeled data and labeled data, I believe most everybody knows here. But just as a simple example, let's imagine images, again, an object in images. Object the object in the image is the label, and just the image itself is the unlabeled data. It's very easy to acquire a lot of images, to acquire unlabeled data. But it's much more expensive to acquire the label. Because what do big companies do to acquire the label? They actually send the images out to people, to humans, pay the humans to label the data. That's very expensive. So one of the questions people ask often in transfer is, would unlabeled data suffice? So if I have a lot of labeled data from the source, is it enough to collect a lot of unlabeled data from the target in order to sort of transfer? If that's the case, good, transfer will be somewhat cheap. But we'll see throughout the talk that maybe it will not suffice. Right. Okay, so what we need to understand at a basic level is the following. What is the relative benefit of source and target data? And what I mean by that is, if I have so much, let's say I have 1,000 samples from the source and 500 samples from the target, what is the performance I can achieve with that? What is the value of the target given that I have so much source? That's, again, the basic question, and we want to quantify that. Okay, so the setup I'll use is the following. And just to make something clear, I'll go back for a second. To make something clear, much of the past theory on transfer has sort of, assumed that you only have the source data and you don't have the target data. So because of that, they cannot answer these questions, right? Because if we are not able to quantify the value of the target data, we just cannot answer the question of how much target data we need to sample, right? Okay, so again, now, like I told you, I'll keep formalizing, and so here I'll continue on the formalism. So now we have data xi, yi, pairs of data points from the source distribution. Let's say we have NP of them, and then we have labeled data also from the target distribution. We have NQ of them. And I'm going to try to see, given any algorithm you want, any classifier you want, how well can a classifier do given NP data points and NQ data points, right? So H hat will represent a classifier learned from sample. And H hat here, my classifier learned from sample, is going to be given both samples. And it can do whatever it wants with both samples, right? It can combine them in whichever way it wants. And we want to understand what error it's going to make on the target. And the error will be simply the misclassification rates. What is the misclassification rate on the target? That's the usual notion of performance in classification. But again, the emphasis here is that that error is measured with respect to the target. How well do I do on the target? Okay, so, and now we want to understand this error in terms of both sample sizes, in terms of NP and NQ. Here again, I'll get back to your basic machine learning, where recall that the more samples I have, the lower my error should go, right, for most algorithms. And so that's sort of what I want to understand here, is given NP samples from the source, NQ samples, at what rate does the error go down as NP and NQ grow, okay? This, intuitively, will have to depend on the distance between the source and the target. How far are they from each other? So somehow, quantifying this error will have to do with the distance between the two things. However, here is a problem. As I started with, the distance between the two things is essentially the information the source has about the target. And we don't really have a way to properly quantify that notion of information, right? Okay, so the right notion of distance remains unclear, somewhat unclear. And here, I'll again try to appeal to your intuition. There are tons of notions of distance between distributions out there. And each notion of distance between distribution serves a particular purpose. So here is a simple cartoon I drew last night. Imagine someone, it was because I kept thinking about going to Mombasa, and I was asking, People, how far is Mombasa? And they ask me, are you going by plane, by train, by car, right? How far is Mombasa depends on the context. So same thing, how far is one distribution from another depends sort of on the context, and the context here is classification, it's transfer, okay? So using a random notion of distance between distribution that was out there, that was created in some field is not going to be enough. We need to come up with a notion that captures transfer. All right. Okay. So let's start by building intuition. What should our notion that captures transfer, what should it do? What should it capture? What intuition should that notion capture? Right. So again, I'm back to this cartoon here. And here is a basic intuition. When is transfer hard or easy? I'll say that transfer is easiest if P, the source, has good coverage of the target, right? If what I care about, this part, is well represented here. So sort of whatever notion we come up with has to capture this intuition that transfer is hard or easy depending on how much I cover the target, the part of the target that I care about. Fine? So how much, and that's all I mean here by how much P, how much mass P has in regions of large Q mass. This is a region where Q has a lot of mass. How much mass does P have in that region? That sort of has to be captured by whatever the notion of distance is. All right? There were tons of results over the last 10 years about trying to capture the right notion of distance. And much of these results, many of them are quite foundational, were able to sort of quantify this intuition for the first time. Many of them went away from the usual notions of distance between distributions that you find in probability theory and try to capture this notion properly. And now I'll go over some of the notions that were out there in the literature, in the theoretical literature on transfer. All right, so common notions of distance between distribution. The first one, one of the most common one in the theory literature, so-called extensions of total variation, right? So total variation will do the following. Let A be any region of space. It could be this region, it could be this region, it could be any region I draw in space. And I'm just going to ask, what is the difference between the mass assigned to A by P and the mass assigned to A by Q? So it's very simple. And the main distinctions, there are many notions that come up in this way, and the main distinctions between these various notions is in their choice of region. Which regions are they focusing on, right? Often, the region that you focus on has to do with the classifier you're using, sort of. Which region of the space is important for the classifier. That's sort of how it's defined usually, okay? So there are extensions of total variation. That's, I'll say, 50% of the theoretical work in transfer. And then there are so-called density ratios, right? So imagine that these probabilities are continuous and have a density, right? Then if they have a density, I might look at any point in space, I might look at the ratio of the two densities and say, okay, if the ratio is very high, maybe the two things are very dissimilar, okay? And so people came up with various ways of capturing the complexity of the density ratio and use that sort of as a notion of distance between the two distributions. So under here, I actually put the names of some of the people who did much of the seminal work here. So what can they prove with these notions? So this is already giving you a sense of there are so many notions we can use, right? And that alone tells you that we still don't know what's the right notion because everybody's trying their notion, right? And I'll come up with a notion, and I won't even claim that it is the right notion, but I'll claim that it is doing well. Okay, we'll get to it. Okay, so the question is, do these notions measure transfer? Right. So here are some of the results. I'll sort of paraphrase much of the results that are there in the literature. So these results are very similar, whatever the notion you're using total variation, DA, density ratio. I didn't talk about this, but these are also, so these are notions of the distance that come from information theory, KL divergence, radial divergence, and such. Wasserstein distance is sort of something that everybody's excited about in machine learning today, and I'll show also that it doesn't work for transfer. So the flavor of the result is the following. The closer P is to Q, the easier transfer, right? So at the very least, we can quantify that. And not only, I'm not saying that if P and Q are close, then transfer is easy. I'm saying the closer. So they are quantifying this thing, right? So the closer P is to Q, the easier transfer is. But this is a one-directional thing. It begs the following question. It begs the question, if P is far from Q, is transfer hard? Because all they said is if P is close to Q, transfer is easy. And I'm asking, if P is far from Q, is transfer hard? And this question is actually very important. Why? Because if I'm using one of those notions, and under that notion, P happens to be far from Q, I'll say transfer is not possible, and I'll give up. I'll go and ask for whole new data sets in Kenya. And maybe I'm wrong, because maybe transfer is still easy. And as it turns out, for much of these notions, P can be far from Q, yet transfer is still very easy. And in that sense, these notions don't capture transfer properly. They are pessimistic. They are overly pessimistic as it comes to transfer. And the reason they are overly pessimistic is because they were not designed for transfer. They were not truly designed for transfer. Even though people have tried to design them from transfer, they designed them based on things that were not designed for transfer, right? They are extensions of things that were not designed for transfer. So here I'll give you some quick examples as to why these notions are pessimistic. So here again, the same cartoon. Recall that total variation, all total variation and DA discrepancy, Y discrepancy, which are extensions of total variation, all these things are doing is the following. They look at regions of space and look at the difference of the mass assigned to that region between the difference between the two masses assigned to that region, right? If I look here, I can make that difference arbitrarily close to 1/2. All right? And 1/2 sort of is the worst case with these notions. I make them arbitrarily far from each other under these notions. Only because I can take this big region and these big regions and the proportions are different enough, and I can just make the proportions so different that I make the two distributions appear very far from each other. Okay? However, think about classification. We are in the case of classification. Think about classification. If I want to, if I'm doing classification, maybe I just want the linear separator, right? The linear separator might go through here. Even though these two things seem dissimilar, if I put a linear separator here, it will work well on the target, right? So in some sense, transfer should be easy because there is a classifier that works well, even though these distributions seem to be far from each other. I hope that intuition is somewhat clear, right? So there is a problem, and we'll try to fix it. Here is another example, and this example is one where I have where the source distribution is this, but the target distribution happens to lie on a manifold, so it lies on a lower dimensional space than the original distribution. Then here, all of a sudden, the notion of density ratio is ill-defined. They blow up to infinity. KL divergence blows up to infinity in these cases. And so what's happening is, under these notions, I'll think that the two distributions are extremely far from each other. Okay? But this is, again, an example where I put a linear separator, another linear separator, they work well. Okay? So in some sense, these notions happen to be over-pessimistic. They can be too pessimistic in measuring our ability to transfer from one population to the next population. All right? All right, so we propose a new distance that will be shown to more tightly control transfer learning, control the rate at which we can transfer. And this is joint work with Guillaume Martinet. One version of it appeared at Colt last year. And I'll paraphrase the notion. It's a bit more complicated than what I'll show, but just for sake of brevity, I'll just give you a sense of what the notion is. Again, it will follow the same intuition as before, that Px needs to give mass to regions that have a lot of mass on the Q. So the source needs to cover the regions that are important under the target. All right? So the notion, we just called it the transfer exponent gamma. And I'll explain this definition in a second. So first, I'll explain just this part, the ball. So the ball is really what you think, just a ball centered at x of radius r. I'm going to look at these balls and then ask how much mass P gives to the ball and how much mass Q gives to the ball. And then I'll say there is a transfer exponent gamma between P and Q if the two masses satisfy this. Essentially, when P is larger than r to the gamma, where r is again the radius of the ball, when P is larger than r to the gamma times the mass on the Q. Okay? So that's the notion. Going back here, I'm looking at the source distribution, the target distribution. I take a ball of radius r, and I'm asking what is the ratio of the masses and whether the ratio of the masses behaves this way. Fine? And then I'm going to ask this question not just about a single r or a single ball, but I'm going to ask the question about all balls on the space and of different radii. Okay? We'll see that this notion, and I'll emphasize it later, this notion is asymmetric. Right? This notion is actually not caring so much about the regions of large source mass, but it's caring more about the regions of large target mass. Okay? Why? Because this thing will hold whenever I'm looking at this ball. Because there's tons of mass here, so definitely the mass here is bigger than the mass here. Fine? Okay? So that's approximately what the notion is saying. Here, for the mathematicians in the audience, I'm assuming that the whole support of the distributions is bounded by 1 and r is below 1 for these things to work out. Okay? So we'll see that gamma, this simple notion, happens to capture a continuum between easy and hard transfer. So it's not just at some corner of transfer, it's capturing a whole continuum from easy to hard transfer. And we'll explain that in a minute. All right. So first, to illustrate the notion, let's look at the two extremes. So gamma is supposed to be positive. So the extreme, I'm going to look at the extreme gamma equal to infinity. When gamma is infinity, we're saying that transfer is very hard. When gamma is 0, transfer is the easiest. Okay? And I haven't proved that yet, but I'll show you the result later. But let's assume that for now. Gamma infinity is hard transfer. Gamma 0 is easy transfer. So what does gamma infinity represent? This is, again, another simple cartoon. Imagine that Px is defined in this region. Okay? Px is 0 everywhere else. And Qx is defined in this region. In other words, Px has really bad coverage of what I can see on the Q. Okay? Then in those cases, gamma happens to be infinity. You can show that in those cases, gamma happens to be infinity. In the reverse case, gamma happens to be 0. But the additional assumptions I'm making here is sort of that Px is uniform on that support, and Px and both of them are uniform on their respective supports. Okay? So this is just a quick sanity check that at least at the extreme is doing what we want it to do. So again, I'm emphasizing this fact here that gamma is asymmetric, right? Gamma is really gamma of P to Q. And throughout, I'm writing it this way. It's not a notion of distance in the way you can think of distance, where the distance between 2 points, whether it's the distance between this point and this point, or this point and this point, it's the same thing, right? It's asymmetric. So why? You can see why quickly here. Well, in this case here, gamma is 0, but if I wanted to look at gamma the reverse way, it will be infinity. Fine? Because one has good coverage about the other. In other words, what this is saying is this, is that I might be able to transfer from P to Q. P has information about Q, but Q might not have information about P. And why am I making this point? Because it takes away a lot of notions of distance that people have been using. So in particular, all the metrics that people have been using will not really capture transfer, because capture is inherently an asymmetric problem. I might have information about one population, but not the other way around, right? Okay. So here's another example. Now I'm going to look at the continuum between 0 and infinity, and what sort of distributions, what sort of pairs of distributions happen to lie in that continuum, right? So in this continuum here, what's happening is the following. I'm letting Q, the target, be supported here. It has mass only here. It's supported here. And then in this case, the source has mass here. It's shifting the mass of the target away to these regions. And as it turns out, one can show that gamma captures how fast the mass is shifted away. It's a measure of how fast the mass is being shifted away from regions of a large Q mass. Here is another example that sort of illustrates why density ratios are not good. So here is the density on the Q, the target, and here is the density on the P. The density on the P is going to 0 really fast. The density on the Q is not going to 0. So if you look at the density ratio, it blows up to infinity. However, we can show that transfer is possible in these cases because gamma happens to be just how fast the density ratio is going to infinity. So gamma is not infinity. In these cases, it could be very small. It's just how fast, essentially, the ratio is blowing up to infinity. Okay? All right. Here is one other example. It goes back to sort of the example I gave earlier, which is that one has low dimensional support with respect to the other. So here, this is P, and then this is Q. It sits on the manifold. And here you can show that gamma happens just to be the difference between the support dimensions. Okay? All right. So back to the examples I used earlier, gamma is much more optimistic than the other ones that we're seeing it so far. Gamma is much more optimistic. In this particular cartoon, where total variation and such are 1/2, you can show that gamma is typically 0, that you can actually transfer, right? As the intuition tells us that we should be able to transfer in these cases. Here again is the example with the low dimension. Gamma, as I said before, happens just to be the difference between the dimensions. So here in this example, gamma is 1, which means somewhat fast transfer, even though under density ratios, under KL divergence and such things, I'll have the impression that these two distributions are very far from each other. But with respect to transfer, they are very close to each other. Right. Okay, so now I'll quantify what I mean by gamma captures the performance limit on the transfer. I've been sort of claiming this so far. And so these are sort of the main theorems we have. Recall the following. And first I need to set up the main theorem, and so a bit more formalism. So we are given labeled source and target data. Source data of size NP, target data of size NQ. Again, we want to understand what is the best possible target performance under any classifier. The classifiers are allowed to use the two data sets, whichever way they want. But what is the best possible performance we can get? The target error, recall, just the misclassification error under Q, under the target. Now, what we'll try to quantify is not just this misclassification error. It is this misclassification error, but it's not just this misclassification error, but it's a misclassification error with respect to the best possible classifier out there. We don't know what this best possible classifier is, but once Q, that distribution is well defined, the target distribution is well defined, there exists a classifier that is best, the best possible classifier. You can imagine this way, that if I had an infinite amount of samples from the target, the classifier I would have used, right? We don't know it. But we'll try to see what is the error of my algorithm with respect to this classifier. And this is something used often in learning theory, and we call it the excess error. In this case, the excess target error. So it is just the how much error my classifier makes over the best possible classifier, which I don't know a priori. Okay? And you can imagine there is a best classifier I want to do as well as possible. I want to do as well as the best classifier. Right? And so this is what we'll try to quantify. We'll try to quantify this error. So this is what the theorem says, the main theorem will say. A first theorem is a so-called lower bound. It's a lower bound. So here I'm paraphrasing the theorem. It just says that under traditional assumptions, and by traditional assumptions I mean various type of classification regimes, various type of assumptions that people have made in classification so far. Under those assumptions, we check under those various assumptions, the following will hold. There exists a rate that is in terms of gamma, such that if I pick my favorite classifier, whatever classifier you pick, there will exist a distribution, a pair of distributions P and Q that are at distance gamma, such that no matter the classifier you pick, it cannot do better than this rate, right? And this rate itself, I'm leaving it this way for now, this rate itself will depend on the assumptions that we make, on the sort of classification regimes that we're in, all right? So I don't want to give too much math, but I'll give you an example of what such a rate might look like. So here is an example. And in fact, this is one of the nicest examples. It's one of the examples that don't look too complicated. So it gives me a rate. So it's a rate under some non-parametric assumptions in classification. It gives me a rate that depends on NP, the number of samples from the source, and NQ, the number of samples from the target. And then you just notice here that gamma happens to appear under NP here. No, here I'm letting gamma be positive. But I'll get to a point where I'll give you examples. Where if you switch, then gamma is infinity. If I switch the target and the source, then gamma is infinity. So in the definition, we say the smallest positive gamma such that this holds. And when you switch, there is no such positive gamma. Okay. And gamma infinity always holds. Because that's a very good question. Let me go back a second. Oh, it's actually, I'll have to go back too far. But I'll get back to that question later. You can tell in the definition that gamma infinity always holds. So if no gamma holds, then it's gamma infinity. Okay, that's a very good question. Okay, so yeah, so I was saying that. So this is one of the rates that we can get, and one of the things to see in this rate is here that if gamma goes to infinity, then there is no contribution from P in this rate. The error I make is only. My performance depends only on NQ, on the target sample, okay? And the reverse, gamma 0, then the rate is very nice. You can imagine that NP is larger than NQ in usual applications. The number of source data that I have is much higher than the target data that I have. All right, so then there is a counterpart of the theorem. This part of the theorem, the first part of the theorem is just saying something. It's just saying what I asked earlier. If gamma is large, then transfer is not possible. That's what I was saying earlier. This is the first theorem. If gamma is large, then my error has to be large. Okay? And this is the counterpart. The counterpart says that there exists always a distribution. The counterpart is essentially just saying that this rate is tight. There exists always, not a distribution, sorry. There exists always a classifier such that for any PQ, the rate, the convergence rate is no worse than this. And then recall again that this here is just an example of convergence rate. In the various assumptions that we have, there are some traditional assumptions under which this rate happen to be very fast. And by very fast, I mean it's like it behaves like 1 over sample size. Here, it's a non-parametric rate. It's not 1 over sample size. It's a root of sample size. Okay? It's a worse root of sample size. But you can get very fast rates depending on the assumptions that you make, and we characterize these rates, these various rates in the result. So I'm just giving you one example of the rate. So there is a distribution, and then here all I put is that, not a distribution, there is a classifier that attains this rate, that is optimal in that sense. There is a classifier that is optimal. And it turns out that it's not a crazy classifier, that for instance, in the case of this worst case rate, this non-parametric rate, classifiers such as nearest neighbors or classification trees and all that can be shown to attain this rate in terms of gamma, to be optimal with respect to transfer. And something that I'll talk about a bit more later, it turns out what's really interesting is that for these classifiers to be optimal, you don't even need to estimate gamma. Okay? In fact, yeah, I'll get to it a bit later. But that was quite interesting to us, that I don't need to estimate these things. And the point being made there is that estimating the distance between two distributions is very hard in practice. Okay? All right. Again, immediate message. Transfer is hardest as gamma goes to infinity and easiest as gamma goes to 0. And this can be verified experimentally. So we just ran a bunch of simulations with increasing gamma. And how do we increase gamma? We use some of the examples I gave you before of the continuum on gamma. And then we increase gamma. And as we increase gamma, we consider different classifiers and try to see, okay, how do they behave? And their error behave as expected, not just on KNN. Any classifier you have, the errors behave as expected. As gamma is increasing, these errors are increasing as the distributions are farther from each other. This is just a sanity check, okay? And one quick message from these things is that transfer requires a lot more source data the larger the value of gamma, the farther the things are from each other. And as a sanity check, it makes sense, right? All right. So here are a few interesting other messages from the same theory. We talked about unlabeled data in the beginning. It turns out that one can show that there are situations where unlabeled data is useless. You can collect as many unlabeled data as you want. It's not going to change the rate. And in those cases, what that means is that you need labeled data in order to transfer. And that's sort of a sad result, a negative result. And the way you show it is that the performance limits we showed earlier are the same. Even if I know the entire marginal distribution, meaning even if I have an infinite amount of unlabeled data from the target. Okay, and by the way, the lower bound is essentially shown. I don't have time to discuss how things are proved, but the lower bound is essentially proved using ideas from information theory. Okay, and the upper bound are proved by taking existing algorithms and analyzing them and seeing, okay, how do they do in these situations? Right. Here is another message we get right away. How much target data do we need to sample? And this was one of the questions that I started with, how much target data do I need to sample? And that's why we try to express the rate in terms of both NQ and NP. Now, by expressing the rate in terms of both NQ and NP, we can see exactly the threshold at which the target data becomes beneficial. And the threshold is given in the different regimes. In the example regime I gave, this is the threshold at which all of a sudden your target data is beneficial. And what we're saying by this is the following, that if you sample less than this, if you have so many source data and you sample less than this, it's not helping you much. You might as well sample, you need to sample more before you see a change in performance, a big change, a significant change in performance. Unfortunately, this is a nice result for theoreticians. We were excited when we got this, but it's not so interesting for practitioners. The reason why is because the threshold depends on gamma, which we don't know in practice. Okay, but I'll get to it. There is a workaround. I'll get to the workaround in a minute. So the next thing here is that transfer can be easy, and that one was interesting to us. Transfer can be easy even if gamma is large, even if px is far from qx. The reason why is because it turns out that if classification under the target happens to be very easy, like there is low noise in the labels and such, it turns out that can greatly benefit transfer. So it's the whole picture is not only the distance between the distributions, but also how hard the problem is to start with. Okay. All good. That's theory, but is this useful for practitioners? I believe that some of these messages are already useful. Practitioners have a sense of what to expect, okay? But here is another question that's quite interesting to me, and that relates to what I said earlier, that we don't know gamma a priori, so what can we do, right? So let's say that I want to automatically decide how much target data to sample. So here is a practical situation. I have so much source data already, and then I have to decide how much target data to sample. I don't want to learn gamma. What do I do, right? I want to sample as efficiently as possible. If the two distributions are far from each other, I sample less. If the two distributions are very far from each other, I sample more. If they are very close to each other, I sample less, and I want to do this automatically. All right? So here is a setup where we can do something almost like that. It's ongoing work. So this is an adaptive sampling procedure, and the setup is the following. I have NP labeled samples from P. So I have so much labeled source data, but now I have a lot of unlabeled target data. And the whole question is going to be, can I pick which ones to label? And can I pick that nearly optimally, okay? So I'm going to paraphrase a heuristic. So adaptive sampling heuristic, this is the heuristic. The heuristic just says, sample in low confidence regions where gamma is large. You can imagine that I define gamma globally, but I can also define gamma locally, right? It's just measuring the ratio of masses, essentially, in regions. So I can define it locally, and so imagine I'm just going to appeal to your intuition without having to give math. So gamma of A, what I'm calling gamma of A here, is it compares PX and QS in the region A. We'll compare them just on balls in that region, right? And that I can sort of estimate. I might not be able to estimate the global gamma, but I might be able to estimate this local gamma. All right. So essentially, this boils down to label, only ask for labels in those regions that I'm not confident in, and only ask for labels in those regions that I'm not confident in, and also there happens not to be so much samples from P, but where there is a lot of samples from Q. All right, and I can observe this just from unlabeled data. All right, there was a procedure by Berlin and Erner in 2015 that sort of inspired this heuristic. And now I'll show you how the heuristic works. So these are some experiments with CFAR10. CFAR10 is this data set that computer vision researchers use, right? And it contains images from cats, dogs, planes, cars, all sort of things, all right? And this is the setup that we'll do. We'll create a target distribution that has 50% of images of cats and dogs. But the source distribution will have much less, okay? And so that's the setup. In this experiment, the number of source data points is 20,000. The number of unlabeled target data points is 6,000, okay? Next, what do? We're actually going to use a nearest neighbor, but we'll use a nearest neighbor on features obtained from a deep neural net. So we take a deep neural net trained on CFAR, code it at the 10th layer, and then use that as our features. And then the problem setup is sort of what I gave earlier. All right. So how do we do? The results are sort of here. The main parts of it that I would like you to concentrate on is random target, which is I just randomly ask for target samples, okay? And this here is what the heuristic I told you about a minute ago. And this is the number of target labels. Number of target labels is just essentially, I'm telling the algorithm, sample at most this many target labels, and let's see how well it does. Fine. And we quickly see that with just 200, I do as well as labeling randomly with 500, right? So going back to cost, if it was costing me, if labeling 500 cost me $10,000, then this simple heuristic is costing me much less than $5,000. Fine, right? And it's a simple heuristic, but that's coming out of the intuition built from the theory so far. All right. The other curves, I won't talk about them much. It's various things I was trying, okay? Various things I was trying, including heuristics that were there. This is the heuristic from Bernard and Erner. And this is a different heuristic that I was cooking up just to see. The point of this heuristic, random target and source, was to understand how do I, once that I've labeled so many target data points, do I throw in back the source data? And what effect does that have? And it was quite interesting that sometimes throwing back the source data can actually hurt me. But I don't understand it theoretically, right? But it was quite interesting. All right, so the best performance is achieved really quickly. And now I'll just summarize what I've talked about so far and tell you a bit about future directions, all right? Okay, so quick summary. This notion of gamma captures a more optimistic view of transferring from a distribution, from a population to another population, right? Much more optimistic than a lot of the notions of distance that people have been using or that theoreticians have been proposing the last 10 or so years. Unlabeled data can only improve in constants, can only improve the rate in constants in the worst case. Adaptive sampling is possible. This is the last thing that I was showing there. Adaptive sampling is possible even without knowing the global gamma, right? We just do this heuristic. I'm still in the process of analyzing the heuristic completely, but we can show that that simple heuristic attains the performance limits. The one thing we were not able to fully analyze is the number of samples that the heuristic will request in the worst case. Okay, we have an upper bound on it, but I don't believe it's optimal. All right. Okay, open directions. One of my, there are tons of open directions, actually. And that's what I was saying earlier, that I'm not going to say that this is the right notion yet. Okay? However, it's a step. One of the open directions is refining gamma. How do I refine gamma? Gamma is still sort of worst case. What I mean by that is that gamma tells me the limit of performance over all possible classifiers, universally, all possible classifiers. Take your favorite classifier, maybe it's deep and N. The limits are those limits. Math don't lie, right? And that's just the limit. However, this is worst case in some sense because I'm looking at all possible classifiers. However, in practice, people are not looking at all possible classifiers. They have their favorite classifiers, and we want to sort of understand what are the limits just within my class of algorithms that I'm going to focus on. Does that sort of make sense a bit? So maybe it's nearest neighbors, trees, all that. That's your favorite classifier. So this is a simple intuition that we've been working on with Steve Haneke for a year now. And the intuition says this: rather, the gamma is defined over all balls in space. Rather than defining it over all balls in space, let's define it over just those regions of space that are relevant to my choice of classifier. All right. So it's a simple intuition, and this is what it gives us. I'll sort of illustrate the intuition with this other cartoon here. Imagine that my set of classifiers, this is my entire space, and my set of classifiers is really just these two linear separators. Then I don't really care how much the two distributions differ over the entire space. I really only care about how much the two distributions differ wherever the classifiers don't agree. Imagine that these classifiers, imagine we have only two classes. This one says plus here, minus here. This one says plus on this side, minus here. They disagree here. And I only really care about where they disagree. Why? Because wherever they agree, the error is the same, under P or Q. Okay? So I'm only going to care about where they disagree. And so we can redefine gamma just in terms of these regions of disagreement. And let H and H prime be two different classifiers. We're going to look at all classifiers within my class, all classifiers that are that can be produced by my algorithm. Look at all those classifiers, and then see really how the mass P assigns to those regions where the classifiers disagree. And that's sort of a redefinition of gamma. And one thing we can show is that this redefinition actually also yields performance limits similar to what I showed so far, but now performance limits that are even less pessimistic, that are very specific to the choice of classifiers I'm making. All right? Okay, so that's one of the open directions. There is another whole open direction that I don't have time to talk about refining gamma, but I don't really have time to talk about it. At a high level, I'll just say there is a sense in which also that I'm looking, okay, I can say it actually. Here I'm looking at all these regions of disagreement, and I want this thing to hold over all regions of disagreement. Maybe we just want it to hold on average. Right, so that's another direction we're pursuing. And so the key of it is we want to refine gamma down to a place where we feel satisfied that it is as optimistic as possible, and really gives us a way to decide how to sample as little as possible. Right. Here is one last open direction. This one is very important. I just haven't talked about it much throughout the talk. So the talk has focused so far on how much to sample, right? But after you sample, you have to do something. You've sampled the target, you have so much source, and you've sampled the target, and you have to do something. How should you proceed? So what are optimal heuristics? Now that I have the two things, what are the optimal heuristics? In people who do transfer in deep learning, one of the heuristics is take the neural nets that you've learned so far, find a place to cut it off well, and then transfer. That's one of the heuristics. Another heuristic that people use in practice is take the source data, the target data, and find a way to reweight the source data such that it looks more like the target data. So there are tons of heuristics people have out there for how to really combine, how to use these two data sets. Right, and one question is, what is optimal? What is the right way? Right, and so we've been thinking about that. It's a tough question, and we only have a partial result. But one good thing about the partial result is that for a lot of the optimal heuristics we consider, it turns out that we don't have to estimate gamma. We don't have to estimate any notion of distance between the distributions. These heuristics are adaptive, automatically adapt to the distance between the distributions. And that was quite interesting to us. So here is one of the heuristics. It turns out that the first heuristic is something that people do a lot in practice. I take the source data, I take the target data, I just combine them. That's my big data set now. And I'm just going to run my favorite classifier. I don't do anything. I just combine them and pretend they are from the same distribution. I run my classifier. Right. So that was interesting to us. Okay, when does this work well? It turns out that we can show that in very hard classification regimes, such as non-parametrics, this is optimal. In extremely easy classification regimes, this is also optimal. We just don't know if it's optimal in between, right? And we've banged our head at it for 6 months. We don't know if it's optimal in between, okay? Yeah, me and Steve, we call each other, we're like, I think it's optimal. No, I don't think. Every week we are like, not so sure. So, but we hope to have an answer. Because if that's optimal, then great. This is all we need to do. It's so simple. It's so, right. Here is a procedure that, it's a theoretical procedure that we show is optimal in most of these regimes. Right. The procedure does the following. It does some sort of constrained risk minimization. Let R hat Q be the risk, my empirical risk on the target data, okay? And R hat P be my empirical risk on the source data. So the heuristic just says minimize R hat Q, subject to R hat P being within a ball of the best classifier under the source, okay? It's not easy to minimize. This thing is not easy to actually implement, but it's optimal. And it's bringing us now to, okay, we sort of see the form that an optimal heuristic should take. Can we make this practical? So that's something still open, right? So, but it's intuitive. It's just saying, I have now my target data, optimize over it, but with the constraint that I don't do too bad on the source. That's all it's saying, okay? And it's also making us feel like maybe Bayesian procedures do something like this, right? It's not so clear to me. I've actually trying to talk to Shakir about it a little bit, that maybe Bayesian procedures are optimal, and maybe Bayesian procedures are really meant for transfer. And in some sense, I feel like it must be true, because what are Bayesian procedures doing? It's saying the more information, I have some information, and I'm not going to believe the information completely, but I'm still going to use it towards making my decision once I see the right distribution, right? And so, yeah, this thing, however, happens to be hard to implement. All right, so the more we work on this, the more we realize that most of the practical and interesting questions in transfer remain open, okay? Let alone the cartoon that I showed you earlier, being able to do transfer like humans or animals do, right? Or like biological creatures do. Let alone being able to do that, even covariate shift, we don't fully understand. And we've only talked about covariate shift while there is much more complex and rich transfer regimes, right, outside of covariate shift. So in covariate shift, my transfer problem is I have a particular distribution. The labels or classes within it are sort of the same as the label or classes within my target distribution. However, there are tons of transfer problems, for instance, where the classes I'm observing in the source are not at all the same as the classes I'm observing in the target. And somehow, practitioners are able to do something even with those. And that's where I'll say that even though I want to praise theoreticians, I'll have to say here that practitioners are always a step ahead, right? They tend to be always a step ahead. However, they come up with so many heuristics, and it's important for the theoretician to try to understand, and I think it's important for the practitioner also to to try to understand which one of these heuristics is best, and that way we can all focus on the best practice over time. All right. Last, I'll say that transfer learning, one of the reasons why it's so important is because it's also related to so many other problems. Multitask learning, curriculum learning, lifelong learning, etc. It's related to all these problems, and I'm hoping that being able to gain intuition as to transfer allows us to gain intuition as to these various other problems. One thing I'll say quickly here about multitask learning is the following, is that remember, I said that transfer happens to be an asymmetric problem. I can transfer from P to Q, but I might not be able to transfer from Q to P. In multitask learning, what people have been doing quite a lot is I have multiple tasks, and I'm trying to find a way to combine them. So I have samples from different distributions. I'm trying to find a way to combine these samples such that I do well on all distributions at once, right? And part of what we're understanding here is that maybe it's not enough to just combine all the samples. Why? Because some of the samples might have information on the other, but not the other way around. And so it might not be the right thing to combine all of them in the way people have been doing often in multitask learning. But we're hoping to gain more intuition over time. At this point, I'll just say thank you. And I don't know quite how to pronounce it. Asante Sana. All right, thank you.
Thank you very much, Samory. I want to ask if anyone in the audience has any questions. We have 5 minutes for questions. Yes.
I have a question on the definition of gamma. Is it only defined in terms of the features or also in terms of the labels?
That's a very good question. It is defined here just in terms of the features for only one reason. That we were hoping to be able to say, okay, in covariate shift, it's enough to define them in terms of the features because the labels remain the same given any set of features, right? Py given x is equal to qy given x. Okay. However, in more general situations, we need to define it also in terms of the labels. And part of the work we're doing with Steve Haneke is coming up with a different notion, which I haven't discussed because I felt like it would be too long. A different notion that also captures the apport of the features. The apport of the labels. Okay. But similar intuition.
That was like when the last exam turns out to be the hardest one.
I cannot quite hear you, I'm sorry.
Your speech was like when the last exam turns out to be the hardest one. So yeah, a couple of questions. So I understand the importance of gamma in terms of like how it evaluates the performance of a hypothesis set. But like you also say that for adaptive sampling, we don't care that much about it. So for pure transfer learning, how much do we actually care about gamma? And my second question is that, so to link about the two parts of your talk.
Can I answer the first question first, and then we go to the second one? So the first question, how much do we actually care about gamma? We care about it for the following reason. I said in the last open direction, we want to know which heuristics are optimal, right? And the whole point, one of the main points of that whole theoretical discussion was to understand what do we even mean by optimal. And what we mean by optimal, we'd first need to understand what are the, what quantities capture optimal performance, and gamma is one such quantity. That's the main reason. However, we then step back and we say, okay, most notions of distance between distributions are very hard to estimate from sample. And it turns out that if you need to estimate that first, it could be even a harder problem than the original problem. And so, hence, we try to come up with ways to do optimally without estimating it. Okay, your next question.
Yeah, my second question was, so to link between the two parts of your talk, so the motivation was trying to do transfer learning, basically. So when you put this work on a paper and you get to the experiments part or the results part, do you focus on the plot with, for example, the target error according to gamma or the bounds, or do you actually try to do that on a data set and like show that we can do transfer learning with such theory?
That was the whole point of the experiment I was showing. Yeah. That it's not just theory, that the theory is allowing us to, is guiding us in what should be the right algorithmic approach. But now, once we believe this is the right algorithmic approach, definitely we have to try it on real-world data sets. I use CFAR10. Some people would argue this is not as real-world as possible. For me, this is a big step, okay?
I'm afraid we have to start with the prize giving. Samory will be at the party. Please grab him with a glass of wine and ask all your questions. Let's give him another big round of applause.
Thank you.
I'm now handing the microphone over to Vukosi, who's going to tell us about the poster process.
Okay. All right, so I wanted a little bit to talk about the process this year of the posters, and just to give some numbers. So, yeah, on the website, we normally have more posters than it actually presented, but this year I think we had less attrition than last year, which is great. So we're hoping to get to like 100%. And actually 110% in the next 2 years, where there's more posters than actually are. So we had about 100 judges. Thank you to everybody who actually participated. It was great seeing all the interactions yesterday, and I hope for everybody also, it was actually a good way to learn about other people's work. I thought of, like, I wasn't going to come up here and talk about this, but I thought it would be actually very much to highlight something that happened yesterday that kind of really characterizes this community. We don't see, okay, I guess I don't see the deep learning in Daba as being something about us, the organizers, or like, you know, people who work around this, but really it is about the community. And this really crystallizes for us. Yeah, so on Wednesday we had a challenge with the poster boards getting here after lunch. They were supposed to be here before lunch. People found out that there was a problem. People gathered, self-organized, and really got all the posters here. People jumped on the back of a truck to make sure they were delivered. And I just wanted to recognize all the guys who helped out with this. At the same time, yes, people got here. The poster boards were everywhere. We didn't have any numbering scheme for the first one. And like, you know, it just became something else. And then again, just because of that, a couple of volunteers came up and they verified what posters were actually up. I think it was Peño, And Gwena, please, thank you, wherever you are here, putting that together. And it was easy then to cross-reference this. And even further, in between this first session and the second one, there were a couple of people who got together and put a new numbering scheme everywhere, and you should have seen for the second session. So thanks to Vongani and the whole team that worked on that, and it's really great. Thanks on that part. And that's been the thing over the years, that every time a challenge pops up, we always can actually rely on everybody else, being us, to actually go solve the problem and then just get on with it, right? That's the thing. We're here to share. Let's, it's not about sitting on the sidelines. To that end, again, very interesting thing over the last 24 hours. For the posters, I said there was 114. We put up on Slack, on Twitter, hey, map your poster to the SDGs. So far, we already have 42 responses, which is incredible. That people can react so fast. If you haven't mapped it yet, check the Slack or check Twitter. We'll see if we'll share it another way, and you can just scan that as well, or go to that URL. It's because that then can be another artifact that we take forward, that just showing kind of where the work that you've presented actually falls in. Another fun poll that happened this week. It became kind of very apparent earlier, for one reason or another, it might have been just a long night, that we started asking each other, what's your Uber rider score? And then it became hey, we could also create a poll at the Indaba for this, just to understand what actually Uber is doing in this space. I do not know who has a 2, but I don't I guess you ask your friends to take the Uber in that part, and that's just most people, I think it's between 4.33 and 4.66. I just didn't update this because people are still actually contributing to it, and you can actually go get the data now on GitHub if you want. Now, please document the Indaba. People have been taking pictures, people have been tweeting. There is still going to be an after the Indaba. We really want to hear if you create a blog post or anything like that, let us know. Email us at info@deeplearningindaba.com if you have things to share, if you have suggestions. That's been one of the interesting things this week also. People coming up to us and saying, hey, I would like to do this today. Or I would like to start this today, and then people, and we're just saying, yeah, just go ahead. We're not going to block that. So it's really becomes really the self-generated conference on the other side. Post on social media, share your pictures, share your thoughts. You'll see later a bit about the post-Indaba survey. Tell people about the Indaba. Tell people about what happened here. Right, just like you told them what happened in Stellenbosch and in Johannesburg before. Right, this was a special gathering, and we want to get people to understand what actually the Indaba is about, because some people have assumptions about what actually the Indaba is, and most of the time when people actually come here for the first time, it's way more than what they thought actually this was. And join the mailing list. We have the Machine Learning and Data Science Africa mailing list, and you can go to that website also to see. It's a conferences on the African continent, but at the bottom you have a link that takes you then to the mailing list. I think that basically will be it from me. And thank you. I look forward to seeing you this evening.
So really quickly, I'm going to take us back a bit because we need to cover some of these announcements just one more time. Okay, so payments. If you haven't paid for accommodation yet, please meet me at the back of this hall when we end this. The closing event tonight, like we said, the buses are going to be leaving from EBR, so the parking lots between the education building and the computer labs. And finally, collect your coupons as you're entering the bus. The lost and found box is it's at the back. Vukosi is taking it at the back now, so if you've lost anything or if you've collected anything that is not yours, please put it in the bag. Breakfast tomorrow is going to be served at KUCC for those who are staying at Nyayo hostels. And again, checking out is going to be at Nyayo hostels. At KUCC. Checking out for all Nyayo hostels people is going to be at KUCC. We've received lots of questions about whether what happens if people are checking out at odd hours in the morning. Still, the process is the same. pick up your stuff from Nyayo hostels, go to KUCC, go to room number 2. Elizabeth, who is organizing accommodation, is going to be available for most of the night and the early morning, so you can check out whenever you need to, and then return your keys to her and collect your deposit. And then finally, if you're looking for someone to go to the airport with, you should find the airport's channel on Slack and possibly coordinate for, split fare purposes. Then we're going to go into the awards ceremony.
This is one of my favorite parts of the Ndaba. We want to recognize research excellence. And so we have a number of poster prizes. And if you see your name, please come to the front. We'll hand over the prize to you and then go to that side to take a picture. So the flow will be across the stage. So first of all, we have a number of book prizes from Cambridge University Press. Will these people, if we go to the next slide, Anna, Devon, and Liron, please come to the stage. Thank you so much for contributing. So Cambridge University Press has not been stingy by sending 3 books. I think there are a few more stuck at customs somewhere. And then next up, MIT Press has been extremely generous in sponsoring 20 book prizes for us. Shahil, Ala, and Devon, please come to the stage.
Batch of MIT book prizes. Mosima, Simone, Nema, Samantha, Gerard. Please come up to the stage.
Okay, now I'd like... Jean-Michel, Joshua, Deborah, and Jeanne, please come on the stage to receive How Smart Machines Think.
Next batch of prizes. Tumisho, Mohammed, Sabrina, Zimkita, Tejumade. You guys are receiving a copy of Deep Planning.
We've got some signed books by Rua Benjamin. Are we going too fast? Let's pause for a second. Okay, here we go. We've got some signed books by Rua Benjamin, Vungane, Alessa, Mariam, and Proskovia. Please come to the stage. Thank you so much for all your hard work. So we've had a fantastic snapshot Serengeti hackathon. I want to give a call out to 3 teams, South AI, Storm Breeze, and Stellafants. Each of them solved a very complicated challenge. Where you are, please just stand and then we'll give you a big round of applause. Then Oliver, guys, the next up is the IBM Zindi Malaria Hackathon.
Brilliant, thank you. Yeah, please come up to the stage. 3rd place, Edwin. 2nd, Lawrence. And Aladdin first.
Some of you may or may not know, but there's been an event that's run in parallel with Indaba this year. That was Teens in AI. The Teens in AI winners, and who's handing over the prize, please come to the stage. Okay, so at this point, every one of you must be asking, what is Teens in AI? A 1-minute Indaba crowd.
Hi guys, sorry I'm breathing. It's breathing too. It's been an intense 3 days. Basically, Teens in AI is to expose teenagers to artificial intelligence and machine learning, and we incorporate that to design thinking in problem solving with the SDGs. And this team, they were tackling SDG number 4, which is quality education, and they won first place. Teens in AI was started by Ayana. Ayana is based in London, and this is the first ever Teens in AI hackathon in Africa, in Kenya. Thank you.
So basically, the past 3 days from Wednesday to Friday, we have been handling the 3 SDGs. We have been doing design thinking, and we learned how to develop models in using Microsoft Azure, machine learning. So we taught them how to do machine learning. We also believe that, like Andrew and G, that AI is the new electricity. So we have to teach even our teens how to do AI. Thank you so much.
Thank you very much. Okay. Do you want to do the next one?
Yeah. So moving into the poster prizes, we have very special awards for the runner-up and then the winning poster. The runner-up poster gets to attend World Summit AI, which is happening in October in the Netherlands, and they get to give a tech talk based on their poster, or the work that they presented rather. And the runner-up poster goes to drum roll, maybe.
There should be a drum roll here.
Ayodele Olabi.
So he's off to Amsterdam in 1 month.
Actually, I'm just a year old in data science. I started last year, May 19th. I started with Data Camp, and I work with MTN Nigeria, and I don't do data science at work, so I only have 8 p.m. to maybe 2 a.m. to work on my poster, and I can't say anything.
So thank you, Ayodele. Through a combination of efforts from the Deep Learning Indaba and the World Summit AI side, he gets a fully sponsored trip to go tell people about his work. Congratulations again.
We also have a best poster prize. Let's. Should we shake hands? Okay. We've got a best poster prize. I'd like Tempest to please come up. Microsoft has been extremely generous to for the second or third year in a row. Second year in a row, sponsored the best poster prize. Some of you might already guess what this is. And it is, and it goes to... Oh, you might wonder what the prize is, but I think you all know. This is a fully paid trip to Vancouver, Canada, to attend Theorems.
Next, I'm going to invite Shakira on stage to speak about some very special awards.
I'll just use this one. Hi, everyone. Okay, good. So let's do this. So the work of the Indaba is obviously driven by a lot of hard work from several people as a fully volunteer-driven community. So this year we wanted to introduce the Ubuntu Prize. Now the Ubuntu Prize forms in all the thread of the philosophy with which we all build the Indaba together. You will remember, of course, the philosophy of Ubuntu, of Ubuntu, of Ujamaa, of the Jama'ah, which comes in the Code of Conduct, which you all know very well. But this also talks about how it is that we actually build communities. So I think you've seen already, and we are very happy on the board of the Indaba to give the Ubuntu Prize for services to the African machine learning community, and obviously to the Baobab team. So please let's give them a round of applause. Please come up to the stage. The Baobab team is Avishka Bupchand, Keleab Tezara, Jade Abbott, Amrit Purushottam, Lindani Ricardo Mabasso, Herman Bernard, Jean-Vincent de Cavallo, Ilse Lawrence, Bushlem Tembu, Sitembile Sindroninia, and Siobhan Hall. And they are given the award for the Baobab app that has significantly enhanced the ability of the Indaba to support its communities. And to the team. And so, thank you all. We celebrate your efforts and contributions. You remind us that Ubuntu and love are real principles that lead to transformative change. Thank you. So, of course, this year's theme was Sauti Yetu. And we didn't tell you much about Sauti Yetu because what we wanted was that you would discover this principle of finding our voice throughout the week. And how you did that was through this week, there were more than 60 speakers who you met who all shared with you their voice and helped you understand where it is that you fit within this landscape of machine learning and artificial intelligence and the things that we do as a community. So if you remember, last year our call was Masakane, we build together. This year we are saying Sauti Yetu. You need to do more to raise our voice in African artificial intelligence. So please continue to build more confidence, take more ownership, and build the responsible technology that we will together use, using those principles of Masakane and Ubuntu and Ubuntu to build the new kind of prosperous Africa to which we are all working. Thank you again.
So an event like this cannot be organized by one or two or three people or even an organizing committee of 28 people. It takes a whole community. So Aldrich and I have a few thank yous which we'd like to acknowledge now.
And my confession is that this is a bit like saying thank you after a wedding. You're always afraid that there's someone you're going to miss. So if we overlook you, please forgive us.
So first to the Indaba X organizers, who in the run-up to the Indaba gathering contributed a lot. Can we give them a round of applause?
In fact, if you were an Indaba X organizer, will you please stand up? Every Indaba X organizer who's here. You are amazing superstars. Then tutors, Tali, James, and the whole tutor team. We've heard such amazing feedback from everyone about how the practicals help forward everyone's journey. Again, thank you so much for all the very, very hard work that you've done. We know it's been long hours, but it's taking us forward. Thank you.
Next. Just another thank you to Avishka and the whole Baobab team for automating one aspect of this conference that has just made all our lives much easier. So thank you again.
We have to say thank you to everyone who helped at the last minute, who jumped on a truck, who carried poster boards, who rallied to organize things, who carried stuff, who's been part of this community through everything this week. Thank you.
To the Kenyatta University team, who we have worked with for very many months leading to this conference and then very intensely during this week. I'm probably going to leave out some of their names, but then just to acknowledge the ones who are on the ground helping us rectify anything that was amiss using the feedback from just everyone. Thank you, Helen, Francis, Lisa, Grace, Harrison, Arthur, Gad, and just everyone from Kenyatta University who's been on hand to make our lives easier.
Next, I'll move to this side of the room. We have to thank our sponsors. There is a whole cohort of companies who believe in the vision of strengthening machine learning in Africa. So again, we want to thank Kenyatta University, DeepMind, Microsoft, the Rockefeller Foundation has sponsored us for the first time, Google, DST in South Africa, Apple has joined us for the first time, Facebook is here for the first time, Africa's Talking, IBM. Thank you, Salesforce, especially for the amazing socks, Comas, InstaDeep. You know, Visa has joined us for the first time, joined this community. Thank you. IDRC from Canada, SIDA from Sweden, Amazon, AI Journal, Netflix has sponsored us for the first time. Carbon, Kaggle as well, Safaricom, Zindi, UCL, Nearmap, Africa Oxford Initiative, Black in AI, our friends there, IntelliPro, Utumarmoja, different publishers and universities, Cambridge University Press, MIT Press, Knowledge for All, especially Davor. Thank you so much. Without you, this would not have happened. You know that. Windsor Hotel and Safari Park Hotel. We'll be going in a few minutes.
So after acknowledging that batch of sponsors, there's an extremely special group. To put together an event like this, there's a lot that goes on in the background, and really a lot would not have been possible without a lot of people pulling invisible strings. In particular, we'd like to acknowledge again Davo and the whole Knowledge for All team, Simon, Kevin, and the wider Exposed team, who we know made loads of sacrifices for us to have this amazing venue that we have. And finally, Tracy and Kevin and the team from Gig, who helped us with the solutions of the payment solution. So thank you again, guys.
I don't know if the team at the back could come to the front of the stage, because you probably can't because you're busy organizing this. Everyone from Expose, I don't know if Simon's here, he's probably setting up the evening party. Expose has been a tremendous partner for this Indaba. There are things that have been fluctuating even at the 11th hour, and they've bent backwards to make this Indaba happen. So the Exposed team, we are extremely grateful for your unwavering support. Everyone at the back, just give a round of applause for everyone at the back.
And we would also like to thank all lecturers and contributors, many of who have facilitated their own transport and accommodation and upkeep during this stay. Thank you for coming and sharing your knowledge and just helping us further strengthen the African ML community.
In fact, very quickly, if you lectured or led a practical or contributed to organizing, will you please stand up? If you spoke at something, we're on a panel. If you're a tutor,
So it takes a village to raise a child, and we have tried very hard to acknowledge our very large village. Thank you again.
So the child is now a toddler that's 3 years old. It's gone through its terrible 2s, now it's in its thunderous 3s. And so I want to say thank you for the organizing committee. I want to call you out all by name, but it's going to take a while. Should we come?
Yeah, let's do it. So there's Ulrich, there's Kathleen.
Where's Miriam?
Maybe everyone can be making their way to the stage as we do this. Mariam, June, Dipali, Victor, Alan, Chris, Rosemary, Miles, Gola, Mary, Betty, Alfred, Richard, Avishka, Vili, I'm like
it's been a long week.
Benji, Daniela, Stefan, Nyaleng, Mudhoni, Karim, Aji, Vukosi, and Shakir.
So this is a team of people that we've had an hour-long meeting with every Wednesday afternoon at 2 o'clock since the last Indaba finished. Well, actually, we had a few weeks off. Some of the people that you've seen on stage did 16-hour days to make this Indaba happen. In my mind, they're not only superheroes, but they're a fantastic, great group of friends. So local committee, core committee that's spread across the world, on behalf of Kathleen and I, we couldn't ask for a greater team to organize this Indaba and take this mission forward. I'm not going to cry on stage, so thank you so much.
So I'll let Aldrich address the elephant in the room, which is where we're going to have the next Indaba.
Oh, yes. Okay, so I was about to send you all to the party bus, but there's one more slide. The next Indaba will be ... Okay, so everyone, we're going north to Tunis. And on that note, please do the last things you have to do. Go to Lost and Found. Speak to Elizabeth if you owe anyone money. Make sure you've taken everything. The party buses are at the back somewhere over there. And we're exactly 6:30. Let's get going.
Oh, but really quickly, guys, before we let you go, we'd really appreciate your feedback, just so that Indaba 2020 can be, 10 times better than this. So if you can take a moment to just take a picture of this screen, take note of the link or scan the QR code, give us feedback, let us know what can be made better, what else you'd like to see at the Indaba next year, and then see you next year when we go further up north. And just thank you for everything, guys. Ha ha ha.